Till now, we have drawn free body diagrams with respect to an inertial frame of reference or non-accelerated frame of reference. When we draw the free body diagram of a mass with respect to an inertial frame of reference, we show only real forces, forces which are actually acting on the mass. When the FBD, free body diagram, is drawn with respect to a non-inertial frame of reference, a pseudo force has to be applied opposite to the direction of acceleration of the reference frame. This pseudo force is given by Fp vector equal to mass into acceleration of the reference frame. Please understand this. This pseudo force is related to acceleration of reference frame, that is observer. Observer is accelerating. It has got nothing to do with the acceleration of the object. In this formula, this A0 vector is acceleration of the accelerated or non-inertial reference frame. This has got nothing to do with the acceleration of the observer. This m is the mass of the body under consideration. This is pseudo force. The best way to understand pseudo force is you are studying in a bus. The bus suddenly accelerates forward. Then you fall backwards. You do not fall backward because somebody has come and pushed you. Right? You fall backward because of pseudo force. In that frame of reference, you experience a pseudo force. Same way the bus is moving. And the bus driver suddenly applies brakes. You fall forward. Again, no one has come and pushed you. In that frame of reference, a pseudo force acts on you. That's why you fall forward. Let us look at this lift. If this lift is having an acceleration A0 upwards, in this frame of reference, a mass m will experience a pseudo force in the downward direction. And that pseudo force will be equal to m into A0 in magnitude. So apparent weight of this body will become mg plus A0. When the lift accelerates upward, you feel heavy. When a plane takes off, you feel heavy. Because the pseudo force acts in the downward direction and the acceleration is upwards of the reference frame. If the same lift is accelerating downwards with an acceleration less than g, the pseudo force will be acting in the upward direction. So therefore the apparent weight will come down and it will be mg minus A0. So if the lift is accelerating downwards, you feel light. When a plane is landing down, then you feel light. If the lift is in free fall, the downward acceleration of the lift is equal to g. The cable has broken, say, right? Dangerous butt has broken. So it will fall down with an acceleration of g. In this frame of reference, your weight will be 0. mg minus g equal to 0. And suppose you're in a real bad situation. The lift has been designed by some bad engineer, right? And the acceleration of the lift is downwards and more than g. So lift is coming down with an acceleration which is more than g. You will fall with g only because you are not tied to the lift. So slowly with respect to the lift you will be going up and finally you will be here. Right? This is all because of pseudo force. Pseudo force is not a real force. It is an imaginary force. Also remember, all problems you can solve without using pseudo force as long as we take an inertial frame of reference. However, in some problems it is convenient to take an inertial frame of reference. It is convenient. However, in some problems it is convenient to take a non-inertial frame of reference and apply pseudo force. But every problem we can solve without using pseudo force as long as we take an inertial frame of reference. Now we'll solve one problem using both methods. First we'll take an inertial frame of reference, that is a non-accelerated frame of reference, and solve the problem. Then we'll take an accelerated frame of reference, that is a non-inertial frame of reference, and solve the problem. So now let us look at this problem. This is one wedge. A triangular block is called wedge. And here is a rectangular block on this wedge having mass small m. The wedge is having mass capital M. This angle is say theta. This wedge is resting on a flat horizontal surface. We are applying a force F like this. And the F is such that small m remains stationary with respect to capital M. We want to find F. How much F has to be applied so that small m remains stationary with respect to capital M? So when this force is applied, obviously this entire system will accelerate in this direction. And how to find acceleration? Simple Newton's laws. Acceleration is always net force by total mass. So what is the net force here? F. Total mass m plus m. So F is equal to m plus m into A. Now only job left is to find A. For this we'll use two methods. First we'll take an inertial frame of reference. Inertial frame of reference means non-accelerated frame of reference. The ground for all practical purposes is an inertial frame of reference. So our observer is here. So this is a nice observer. Now this observer is drawing free body diagram of that rectangular block M. So M is having mass, so weight will act vertically downwards. M is pushing against that wedge. Normal reaction will act perpendicular to the surface. Any other force? No. And the acceleration is in the horizontal direction. In most problems, we resolve mg into components because in those problems the block accelerates down the plane or up the plane. But in this case, the acceleration is horizontal. So now therefore we resolve n into components. Whenever we are doing something, we should know why we are doing it, right? That's why we are resolving n into components, because the acceleration is in the horizontal direction. What will be this component of n? We can easily check that and find out that this angle will be theta. Therefore, this component is n sine theta. And that component is n cos theta. Component in the direction of known angle is the cos component. Component in the direction of unknown angle is always sine component. You can easily see this line. If I draw a line perpendicular to the inclined surface. This is theta, this is 90 minus theta, therefore this will be theta and this will also be theta. So this angle is theta. Easy. Now there is no acceleration in the vertical direction. Therefore n cos theta must be equal to mg, balancing forces in the vertical direction. In the horizontal direction there is only one force, that is n sine theta, and therefore n sine theta will be equal to mass into acceleration. We have got two equations. We can divide the two equations and get rid of n. We will prefer dividing equation 2 by 1 because we like tan more than cot. It makes no difference. But we can divide equation 2 by 1. So we will get tan theta equal to A by G. And therefore A is G tan theta. Simple. We can put it in this equation and find force. Force will be equal to M plus M G tan theta. We have solved the problem. no pseudo force, no non-inertial frame of reference. We got the answer. Now let us put the observer on the wedge. The observer is, say, some mosquito, fly on the wedge, right? So now this observer is looking at that block M, and this observer sees no acceleration of that block because he and the block have got the same acceleration. If you're inside the bus, you don't see the acceleration of the bus because both you and the bus have got the same acceleration. So now we look at this block again. The only thing that I change is the observer. M is having mass, weight will act vertically downwards, right? M is pushing against the surface, normal will act perpendicular to surface, right? As it was earlier, no difference. Now because the observer is accelerating, he will apply a pseudo force opposite to the direction of acceleration of himself, observer. And that pseudo force will therefore be in this direction, MA. Because he is having an acceleration of A in the forward direction, pseudo force will be in the backward direction. And that pseudo force is given by mass into acceleration of the reference frame, that is the observer. Now we resolve n into components as we did earlier. This will be n sin theta and this is n cos theta, same logic. Now with respect to this observer, this mass has got zero acceleration. So vertical forces have to be balanced, horizontal forces have to be balanced. So what will be n cos theta? N cos theta will be equal to mg. And what will be n sin theta? That will be equal to ma. And see the beauty. We have got the same equations, right? Whatever we got using inertial frame of reference, same equations we have got using a non-inertial frame of reference. The only difference is here you realize that n sin theta is the net force, that is equal to mass into acceleration. Here you realize there is a pseudo force ma acting in the opposite direction, so n sin theta equal to ma. Mathematically you get the same result. Only thing that you get there is that you can see ma in the free body diagram. Here in an inertial frame of reference, ma was not there in the free body diagram. And rest of the solution obviously will be same. We will get f equal to m plus m g tan theta. So remember, every problem we can solve without using pseudo force, as long as we take an inertial frame of reference, a non-accelerated frame of reference, that is the observer is having zero acceleration. However, at times it is convenient to take an accelerated frame of reference, that is a non-inertial frame of reference, and apply pseudo force. That way you can visualize the things more easily and get the solution more quickly. So this is pseudo force. Pseudo force is an imaginary force that we apply when we take a non-inertial accelerated frame of reference. And it is important to remember that every problem can be solved by using both the methods. This pseudo force is always opposite to the direction of acceleration of the observer, that is reference frame.